Okay, we're continuing on here. We're talking really the main sort of calculation of the season, which is ice tables. And again, I for initial, C for change, and E for equilibrium here. Again, usually the change is represented with an X, and that's usually what we're looking to sort of solve for. So when you have an equation, you would put your initial concentrations in. And a lot of times, again, if you're not given any information about the products, it is usually safe to assume that you have zero of it to start with. Because you would have zero in this case, as we talked about last time, you could also safely assume that this reaction should be heading towards the right. That means our reactants should be decreasing with time, and that is represented by minuses, while our product should be increasing with time, which is represented by plus signs. Remember that the change part is really the important part because that is what you're solving for, but it also takes into account the stoichiometry, the mole-to-mole relationship of everybody in the equation. So when we do this, this is going to be minus 2x minus x, and this would be plus 2x in this case. At equilibrium, we would take everybody down here. At this point, we would use our equilibrium expression. And what we would be looking to do is whatever it equal to, we'll just call it 100. We would take everything that's on the equilibrium line here and basically put it into there, and we would solve for x. And again, there's a few different ways that you can solve for x. We saw a couple last time. One way is you can use like the quadratic there, ax squared plus bx plus c is equal to 0, where x is equal to minus b plus or minus the square root, b squared minus 4ac divided by 2a. So again, as we talked about as we saw last time as well, that will yield you two x values. Again, to sort of figure out which x value you do not want to use, it is obviously when you do get that x value, that is all the x values that you see in your table. So one of those x values will lead you to a negative concentration, or if you're doing this with pressures, which you can, you would have a negative pressure, which you cannot have, obviously. So that would not be the one to choose. You would then choose the other one along the way. Speaking of that, if you did an ice table here, you can again just do it in pressures. As we talked about earlier, you do want to make sure that they are in atmospheres when you do the ice table. If you are going to do it in pressures, you do the exact same thing with your Kp value, but definitely want to make sure they're in atmospheres when they go into the ice table and do the calculation. Um, once you do that, you obviously can get everybody's equilibrium concentration. We also saw an example where it's actually a perfect square, so you could do a perfect square on both sides and square root it without doing the quadratic if you have that situation occur. Another thing that we also talked about before this as well was Q, and Q is calculated the same as you do K. The idea of Q is, again, what's known as the reaction quotient. It helps us really answer two types of questions. It helps us answer whether or not we are at equilibrium or not at equilibrium. And again, you can only calculate Q if you have basically everybody's information in the equation. So if you do and you are not at equilibrium, it will also tell us which way you need to go to reach equilibrium. So if Q is greater than K, you're not at equilibrium, but you will need to go towards the reactant side to produce or reach equilibrium. If Q does equal K, then you are at equilibrium at that point. And lastly, if Q is less than K, you again are not at equilibrium. And in order to reach equilibrium, you do have to go towards the product side to do so. Questions on any of that stuff we did last time? Remember as well that it is ultimately math. So when you do get everybody's equilibrium concentrations or pressures, you can sort of check yourself by putting it back to the equilibrium expression, and it should equal, obviously, pretty close to the equilibrium constant value. Maybe slightly different with some rounding, but should definitely be in the ballpark of what you see for the K value. Any questions? All right, let's take a look at another one here. Yeah, we'll do this one. If the Kp is 4.31 times 10 to the minus 4, for this reaction. What is the equilibrium pressures of everybody? If you started with 0.862 atmospheres of N2 and 0.373 atmospheres of H2, as I just mentioned, even though their pressures and their Kp, it works the exact same way as concentration. So you do the ice table the exact same way. So why don't you give it a go, see what you come up with in this case. Okay, let's take a look, see how you're doing on this one. So once again here, as I mentioned earlier, we do have a KP given to us. We do have some partial pressures given to us. And once again, our pressures are in atmospheres, which is again what you do need if you're going into an ice table. And as I may have mentioned before, even if they kind of give it to you in some different pressure unit, and they even want the answer in like torr or millimeters mercury, when you go into the ice table, you just have them in atmospheres to do it and then convert them afterwards. So it works really the same way here. So let's just flip the page here. We'll borrow that there. So we can write our Kp expression, which in this case is the partial pressure, and we are going to square it there of NH3 divided by the partial pressure of N2 and the partial pressure, we're going to cube it there of our H2, and that's going to equal 4.31 times 10 to the minus 4. We can do our ice table here. So initially we got 0.862, I think, atmospheres, 0.373. And again, nothing mentioned about the NH3, so we could assume it's going to be 0. Also, that makes our sort of change part pretty easy to make sure we're right. Reaction should be heading to the product side since we have no products to begin with. So this is going to be minus x. This is going to be minus 3x once again here because of the coefficient. And on the other side, we're going to go plus 2x over there. At equilibrium here, carrying everybody down, we're going to get 0.862 minus x, 0.373 minus 3x, and 2x. Any questions on the table here? Like we did previously, we're going to take all that into our expression here, and that's going to give us here a 2x squared divided by 0.862 minus x and 0.373 minus 3x, and we're going to cube that one there. And that's going to equal 4.31 times 10 to the minus 4. All right, so we got some squaring, we got some cubing, we got some, nobody wants to do that. We probably should just go to the next problem and skip this one, I think, right? All right, so let's see if we can figure out a way here we don't have to really do all that math. So when we have a situation like this, there's a couple things we could kind of think about. And one thing that we could definitely think about is our K value here. So when we look at our Kp value, is that Kp value or just K value in general? Is that considered a large value or a small value? It is considered a small value. And because that is considered a small value, we would expect mainly reactants or products at equilibrium. Yeah, we would expect mainly reactants. And what that means is because the equilibrium constant is a small value, we would expect everybody to kind of be hanging out over here on the reactant side. That means that the change that's going to occur as it goes from reactants to products is going to be relatively small. And it can be so small that we can do an assumption and we could assume that x is equal to 0 in this case. Now, we cannot get rid of all the x's. We are only talking about x's that we are going to subtract from a number or even add to a number. And in that case, that would be this x here and that x there. We cannot assume that this is x for two reasons. The obvious reason would be we then have no more x's to solve for, so there's nothing left to solve for. But the other reason is we started with 0 of that guy, right? So if you start with nothing and you get even a little bit, significant, right, from where you started since you had nothing. But the more logical answer is if you get rid of all the x's, you have nothing to solve for at this point. So what that's going to do then is basically reduce our sort of equation here down to 2x squared 0.862 divided by 0.373. Still got a cube it though on the bottom. And that's going to equal 4.31 times 10 to the minus 4. I think I would much rather solve that one than the previous one above on top there. So if we do that, I'm going to kind of clean up some stuff here. We'll go 4x squared there up on top. We'll go 0.373 and we're going to cube it. And we're going to times it by 0.862. That's going to give us something like 0.0447335 on the bottom equals 4.31 times 10 to the minus 4. We obviously are going to then multiply that to the other side. And when we do that, 4.31 to the minus 4, that's going to get us 4x squared is equal to 0.00001928. I'm going to do two things at once. When in this order, I'm going to divide by 4, and then I'm going to come back and take the square root afterwards. So I'm just going to do both of those, one right after each other. So timesing by 4, and then taking the square root. That is going to give us a x value here of 0.00878 in this case. First off, any questions on that there? All right, so when we do make this assumption, there are a couple of things that we do want to be sure of, and that is our assumption good or bad? So when you do make this assumption, you cannot just always assume that it is a good assumption. You do have to check your assumption. So to check our assumption, we're going to use what is known as the 5% rule. And the 5% rule is how we check our assumptions when we make it. So to check your assumption, here's what you do. You basically take the x value you just got, which would be this guy, and you're going to divide it by whatever you are going to subtract from. So that is 0.00878. 0.00878. We're going to divide it by, for example, 0.862, which is our initial pressure here. 0.862 and times it by 100%. And if you do that there, going up about 1.02%, which is a good check. It is less than 5%. To be truthfully honest with you, you can check all of them. So you can check them all if you want. You can take 0.00878. I'm going to times it by 3 because when I go back, that's essentially what I'm doing here. And I'm going to divide it by 0.373 times 100%. We hope we should be good. Truth be told, you really don't have to check them all. Usually, if one is good, then the others should be good as well. So even at that, we're at 7%. No, that's not right. I feel like a math is wrong here somewhere. What did I forget to do? Let's see here. Seven, three, Q. Yeah. Yeah, I feel like I did something wrong here as well. I agree with you. So let's see here. So are we good up to this part? All right, yeah. Everybody got left up there? Okay, so I should divide by 4 here, right? Then I should take a square root. That looks much better. All right, so I'm not sure what button I was hitting before, but clearly not the right button there. All right, so we're good up to here, I think. 0.00220 sounds better, I think. There we go. I failed math. It's okay. Failed chemistry too. It's all right as well. It's reassuring. 220. That looks more like it. Yeah, good. Yeah, okay. Thank you. All right, so I knew something was not right since my seconds check was over 5%, and that's not usually right. So let's try this again here with the right numbers. We'll just cut that out of the video. Nobody will know. So, all right, let's see. All right, so try with our right number here, which is 0.00220. I even did it twice. That's even worse. 0.00220 divided by 0.862 times it by 100. All right, so on this one, that looks more like it. 0.25% basically. So that check is still good. And then again, if we pop our guy into here, unlike the last bad one I just did, we should be good here as well. 0.373 times 100. There you go. About 1.77%. Also a good check. Yeah. So it helps if you get the right answer and check the right answer along the way here. So you can see here, and like I was saying before, usually if one is good, they're all good. You don't necessarily have to check them all, but you definitely should check one because, again, it may not always be a good assumption. If the assumption is not good, you do have to go back and solve it some other way. And for us, that would probably be the quadratic formula that you probably have to go back and sort of solve it using. All right, now that we checked our assumption, we even have the right x value. We can now get our answers here. So we're going to pop that in there and we'll go with our partial pressure of N2 at equilibrium would be 0.862 minus 0.00220. And these are atmospheres, right? Sister pressures. 0.862 minus 0.00220 and 0.8, call it 60. For our H2 is going to be 0.373 minus 3 times that X value, 0.00220. And that's going to get us here. Looks like 0.366 atmospheres. And lastly, I'll just go over here to the left. Partial pressure of NH3 is going to be 2 times X, so 2 times 0.00220, and that's going to give us 0.00220, 0.0044 atmospheres. That particular case there. Those should be the equilibrium concentrations of everybody. And once again, like normal, if we put them back into our expression, we really should end up with the same K value as we had there. So 0.00, better check the way today is going. There we go, divided by 0.366 to the third. Divided by 0.860. That looks like 4.6. That's pretty close. It's pretty good. Any questions on that there? Yeah. Mm. No, the assumption is always going to be you're going to assume X is going to be. So why did I not do the assumption on the previous examples we did the other day? We look at the previous examples the other day, right? We had a K value that's 7, right? We had a K value that's 54.3. Those are considered large values of K. And with large values of K, we would expect mainly products to be there at equilibrium, which means our change is going to be significant, right? So again, you can only try the assumption if your K value is considered small. And that means, again, less than 1, basically, you could give it a go. It will not always work. So you definitely should show your checking of it and make sure that you do check it. There will be a number of places where it may not work, but there will be a number of places where it will work, and it can save you some time as well. So you usually don't have to go too far into it to sort of figure out if it works or not. So sometimes it's a good approach. But again, only for small ones, we use our 5% rule on that. Any questions on that there? So we've seen basically 3 different ways that you could solve sort of these problems. You can obviously do the assumption if you have a small K value. You use the quadratic pretty much always. And you could also, in some cases, like that second problem we did last time, could have a perfect square. You could do it. So those are the three ways that we'll solve these problems. There is another way that sometimes people will solve these problems, which is known as successive approximation. And that's essentially where you go, well, I know my x value has got to be less than like 0.862. So you throw in an x value for every x but one, and then you solve for x. And then you keep throwing in numbers until the number you throw in and the number you get out are the same. And it can be a very long process if you screw that up very badly. You're not great at that. So we will not do successive approximation, but if you look in books or sometimes solution guides, they will use successive approximation as a way to doing that. But we'll strictly kind of use those three methods that we talked about in this class. Any questions on how to solve these problems? Yeah, there it is. All right. Final thing we're going to talk about in this chapter is Le Chatelier's principle. And Le Chatelier's principle is basically this idea that you have a system that is essentially at equilibrium, and then basically you do something to it to frankly screw it up, right? And you add what they call a stress to the system. And some common stresses that you could add to a system are, so you could do something with the concentration. You could do something with like the pressure or volume. You could also do something with the temperature, and you can maybe even add a catalyst. So these are some common sort of stresses that you could add to a system that's at equilibrium. So basically the idea here is you have a system that is at equilibrium. And again, you do something to this reaction. And again, as we know, when we're at equilibrium, the rate of the forward direction and the reverse direction will equal each other. So you do something to mess it up. And as we talked about earlier in this chapter, these reactions are sort of self-correcting. So as you kind of screw it up, it will basically try to find its way back to an equilibrium condition. There's really three things that it will typically do, and you typically talk about when you're doing Le Chatelier's principle, which is in order to get back to equilibrium, sometimes the reaction will be referred to as shifting to the right, which basically means that it's going to make more products to get back to equilibrium. It could shift to the left, which obviously would mean the opposite there. It would need to make more reactants to get itself back to equilibrium. And then there really is a third option that does pop up occasionally, and that is even though you kind of did something to it, there actually will be no change that will occur. So, it actually will not shift to the left, will not shift to the right. Now, obviously, when we talk about left and right here, we're talking about the equation, the way it's written, or reactants and products. Clearly, if you have this system at equilibrium in a beaker, you just have things floating around, right? There's no like a right side of the beaker, left side of the beaker. So we do it in relationship, obviously, to the equation of what's happening here. So let's talk about each of these and sort of what happens in each of these situations. So let's just say that we'll start with concentration first. And with concentration, there's basically two things that you can do. You could either add more, and when we add more concentration, that will always make it shift away from the side we added it to. So add away, AA is a good way to remember that, and it will shift away from it. You add reactants, it goes towards the product side. You add some products, it goes to the reactant side. Adding more concentration is a pretty simple task. You usually just go to the reagent shelf, grab a bottle that has it in there, and you drop it in your solution, right? Not the bottle, but the reagent into your solution, and that will be like adding some ions, right? So if you want to add some silver ions to your solution, you grab some silver nitrate, you add some drops of it in there, you just added some silver ions to your solution, and it goes. The other thing you could do is remove. And when we remove something, it actually will shift towards the side. you removed it from. Now, a lot of times we are talking about sort of solutions, and we have solutions where, in case you're not familiar with, ions are in the solution, and ions are basically floating around, basically. And that's where you find all the ions basically floating around in the solution. Now, if I wanted to remove, say, an ion from solution, do I just reach in there with my hand and grab it out? That is the right safety answer there. That is a no on that for anybody listening as well. Don't reach your hand into chemicals. So you can't really just go in there, right? So how we remove something is a little bit of a different sort of property, right? What I could do in this particular case is I could add something to this solution. Let's just say I added a different positive ion. Here, let's make it red here. Let's say I added something that has a different positive ion here that's red, and it comes in, and maybe that reacts with the negative ions that are present, and those guys then kind of precipitate out as a solid, right? And you make a precipitate. And that's essentially like reaching in there and taking out those ions, because as we know, right, things in the solid state are not going to participate in equilibrium. So it's essentially just like removing that. So that's a very common way to remove sort of ions from solution, is to add something that will precipitate out one of those ions, like using your solubility rules, and get it out of solution as a solid. And again, that's a very common way to remove it. Another very common way that you could remove it, and unlike maybe the precipitate example where you would probably be able to see that you did that, let's just say you had a solution that maybe was an acid sort of base solution or something, and there's some H plus, say, in the solution. And if I had something that's just said had H plus in the solution, and I added some, say, sodium hydroxide. Sodium hydroxide is a source of sodium and hydroxide. So when I drop hydroxide basically into the solution, the OH minus and the H plus will come together and make our friend water. It probably won't jump out of the beaker like I drew it, but it will make some water. And water is a pure liquid, right? Which also is not included in the equilibrium. So this would be a way that you could remove some H plus ions from solution, and you would make water. Might not be able to visually see you made water, but that's essentially what will happen. There might be something else that may occur that would allow you to see it. So maybe a solid would form or something like that, but or an indicator would change color. But that's a very common way. So if you have sort of an acidic solution that has H plus floating around, you could add something like sodium hydroxide or a base, and that's a way to remove H plus ions. Same thing if you had a basic solution that had OH minus floating around, you could add an acid and it would do the same thing. It would produce water, and that would be essentially like removing either H plus or OH minus from the solution, depending on what you have. Any questions on that there? Now, we could think of this like, we have a system at equilibrium here, and we got some advanced stick figures because, they have faces, right? That's the advanced class. The beginner class has no faces. And we'll say this side is my reactant, and this side is my product. And we'll just say we're at equilibrium, right? So we're at nice and equilibrium in this case. And all of a sudden we decide, hey, let's just let somebody hop on this side here. And when they hop on this side, this is what's going to happen, right? We obviously just kind of messed up our equilibrium for sure. Do we need more people on the left-hand side or the right-hand side to balance this back out? Yeah, we need them on the left-hand side. So we added on the right-hand side. It's going to shift away from the side we added it to, right? And now it's going to come back to equilibrium at this situation here. And we're back to, again, an equilibrium position here. And you can kind of think of it the same way if you were to remove something. So if we had our kind of starting position here at equilibrium. Again, that's our reactant side and that's our product side. And let's just say this guy decides to hop off. What's going to happen is this, right? Now in this situation, we need more people on the right-hand side, right, to get us back to equilibrium. So we remove from the right. In this case, we're going to shift to the right, the side where we removed it from. And now we will get back to an equilibrium sort of condition at this point. Questions on that there? Yeah. Chemistry with stick figures, just good stuff. All right. So let's continue on then and talk about another sort of effect that happens. And this has to do, a lot of times these are tied together, and that is pressure and volume. So when we're dealing with pressure and volume, you should think of a relationship that occurs. And usually when we're dealing with pressure, we're dealing with gases. And as the pressure goes up, what happens to the volume? It goes down. That's our friend Boyle's law right there, right? P1V1 equals P2V2. So what happens in this situation is the change that's sort of occurring is the pressure is starting to increase. So what we want to do is kind of bring the pressure back down. But now what we have though is a small volume, right? So if I want to bring the pressure back down in a small volume, would I need more gas molecules to do that or less gas molecules? What do you think? If I have a really small volume and I put a lot of gas molecules in there, what will happen to the pressure? It should increase, right? Because there's going to be a lot more collisions. They have nowhere to go, right? They're all on top of each other. So that's going to create a lot more collisions. So in this case, because the pressure is increasing, I kind of want to bring it back down. So in this particular case, in a small volume, you will shift to the side with the least number of gas molecules. So less gas molecule is going to bring the pressure back down from it jumping up high. And opposite is true if your pressure decreases, your volume has now increased. So you have a much larger volume in this case. And sort of the change that's happening is the pressure is dropping. So we want to kind of bring the pressure back up. So once again, in that larger volume, we would need more gas molecules to bring the pressure back up to cause more collisions. So it would shift to the side with the most gas molecules. This is obviously dependent on the reaction or equation that you're looking at. You have to look at each side and count up the gas molecules. You could do that by simply looking at the coefficients for anything that has a G next to it, right? So anything in the gas state, add the coefficients. It'll tell you how many gas molecules are on each side. Any questions on that there? So if I had 2A plus B goes to 5C in this case. For each of these, what will happen? Will it shift to the right? Will it shift to the left? Will there be no change? If I do the following, let's say I add some C, I remove A, I decrease the volume, I let's see, decrease the pressure, I add B. All right, so take a moment there for each of those. Which way should this reaction shift as a result of doing each of these things? Okay, so we're going to add more C. So we got C over here. When we add, it goes away. So we add it to the right-hand side, should shift away from it, and should go to the left-hand side. The reason it's really doing that is we now have more products than reactants. So that's going to kick off the reverse reaction, right? To have it go in that direction and head towards the left-hand side. If I remove A, It is like creating a hole over there on the outside, and you want to fill the hole, so it's going to shift towards it, which means it will shift to the left in this particular case. The real reason is the exact same reason. When you remove A, you now have more products than reactants, so that's going to cause the reverse reaction to basically occur in this case. So it's going to head to the left there. When we decrease the volume, that means our pressure is actually going to increase. But I always look at volume myself here. So small volume means less gas molecules is what you're going to need there. As the pressure goes up, we want to bring it back down. So when we look at this, that is 2 gas molecules there and 1 there. That's a grand total of 3 gas molecules. This side, there are 5 gas molecules. And we are looking for less. So it will shift here to the left. Yeah. Any questions on those so far? Looking at the next one, we're decreasing the pressure. That means in terms of volume, that's going to increase the volume. So again, larger volume means more gas molecules. So we just figured that out a second ago. We're going to go to the right here. And lastly, we're going to add some more B. So when we add, it goes away from the side we added to. We added to the left, it's going to shift to the right. The deal here is we now have more reactants than products. So that's going to cause the forward direction of that reaction to occur, and it's going to go to the right. Questions on any of those there? So this is kind of like what we were talking about at the very beginning of this chapter. You want to kind of think about what are you going to kind of kick off, right? Are you going to kick off the forward direction? Are you going to kick off the reverse direction? Or is not too much going to happen? Now, let's just say, for example, I had this as my reaction. And I increase the pressure. What's going to happen in this situation if that was my reaction? We'll go to the left, we'll go to the right, will there be no change? It would be no change in this case because when we look at the number of gas molecules, there's 3 here, right? And now there is 3 there, right? So that is a tie. So there is no kind of more or less. So this is one of the ways that you could get a no change to occur if you're comparing something like volume or pressure and you got equal number of gas molecules on each side. There is again no kind of bigger or smaller sort of number of gas molecules. Any questions about there? All right, the next thing we're going to talk about is temperature. And temperature works the same as concentration. And what that means is if you increase the temperature, it will shift away. And if you decrease the temperature, it will shift towards you or towards us, not you, maybe, but it'll shift towards. So how do we know sort of where the temperature is in these type of reactions? And it really has to do with what type of reaction you're dealing with in terms of is it a exothermic reaction, which means, as hopefully you know, heat and energy is released. I would say in most cases, if it's an exothermic reaction, they usually will give you the delta H of that reaction. That's the change in enthalpy, as you may remember from 50. And if it is an exothermic, would we expect our delta H to be positive or negative? It should be negative, yeah. And I would say that's probably the most common way that you'll be sort of told this is exothermic or endothermic is they'll give you the equation at the end. They'll just say delta H is negative 400 kilojoules or something like that. Obviously, what that really means in terms of sort of Le Chatelier's principle is this. If it is a exothermic reaction, you can consider heat and energy as a product. Not correct in all aspects, but for this purpose, it's good. So if you have an exothermic process, you could think of the heat and energy as a product, which means if it is exothermic and you increase the temperature, it will shift away from the product side and go to the reactant side. And if you decrease the temperature, like you put all your test tubes on ice, it will go towards the product side in this case. And opposite is true here if we're talking endothermic. Obviously, heat and energy is absorbed, and our delta H in this situation is going to be a positive number. And what that means in terms of Le Chatelier's principle is we do think of energy as a reactant and not a product. So we think of it as a reactant. And again, so you would have sort of the opposite effect in this case. If you increase the temperature, you will shift away from the reactant side, go toward the product side. In an endothermic reaction, if you decrease the temperature, it will go towards the reactant side. Again, in this situation, you can think of it either sort of increasing reactants or decreasing products. Questions on temperature. Last thing, stress that you could do to a system is you could add a catalyst. And as we've talked about with the catalyst before, again, it is not a reactant, right? It is not a product, and it does not get used up in a reaction. Is there typically to allow the reaction again to sort of proceed a lot faster, a lot more efficient? The effect it has in terms of Le Chatelier's principle is a good effect. It is a no effect, basically, a no change situation. So that again is another way that you could kind of get a no change. You'll just get to equilibrium quicker, but will not cause it to kind of shift really one way or the other. So those are two common ways that you could kind of have a no change, add a catalyst, equal number of gas molecules. Another way as well is sometimes if you add a noble gas. Noble gases are chemically inert. They don't react with other things, right? So that's another sort of situation where you might have a no change situation. If you had a gas mixture, maybe you added a noble gas to it or something like that, would cause no change. Any questions on that there? All right, so this is obviously what we've been talking about. Again, concentration shift away if you add, go towards if you remove. Temperature, again, exothermic or endothermic is really what you want to look at. And remember, temperature really is the only thing that changes the value of the equilibrium constant. Pressure, again, I would think of pressure in terms of volume and just goes with the volume. So small volume, less gas molecules, larger volume, more gas molecules is an easy way to kind of remember that. So let's take a look at this one here. Let's just for fun say the delta H, and this is definitely not the right delta H, but just for this example here, we'll just throw it there. All right, so for everything I'm going to do this thing, again, we want to know, will it shift to the left? Will it shift to the right? Or again, will we get kind of no change occurring? All right, let's see. Let's do increase the pressure. We're going to add N2. We're going to remove NH3. We're going to decrease the temperature. We will add catalyst. We will add some H2. And we'll increase the volume. All right, so take a moment and see what happens for each of these. Okay, let's take a look. So we'll start with our pressure here. So again, pressure, volume sort of tied together. High pressure, small volume. Small volume means less gas molecules is what we're looking for. So here, that looks like 4 gas molecules. Again, just counting up the coefficients or anything with the G. And 2 gas molecules. So that should send it to the right-hand side here. Adding N2. When we add N2, we're adding to the left, add goes away. That's going to cause really the forward reaction to occur because now we have more reactants than products, so it should go to the right. Removing NH3, it goes towards where we removed it from. Again, by removing NH3, we once again will now have more reactants than products, causing the forward direction of that reaction to occur. We decrease the temperature. Looking here, that's a negative delta H, which tells us it's exothermic. That means heat would be considered a product. And in this case, we are lowering it. So that would be like removing our heat. So it's going to go towards the side we removed it from, and it is going to go to the right in this case. We're going to add a catalyst, which will have no change. Here we're going to then add H2, which is over here on our reactant side. So once again, we're going to really go away from where we added it to. And again, the reason again is more reactants than products causing the forward direction to occur. Lastly, increasing the volume, big volume, more gas molecules. That is the left-hand side in this case. We go that way. Any questions on any of those? Yes. Can I explain the lower temperature why I went that way? So temperature works the same way as concentration. So if you increase the temperature, it will go away from the side where sort of heat and energy is. If you decrease it, it'll go towards it. So in this case, because we have a negative delta H, it tells us it's an exothermic reaction. So we could kind of think of heat and energy as being a product. So when we lowered the temperature, it'd be essentially like removing products, which essentially would mean, again, it's kind of the same idea. You kind of have more reactions to products and cause the forward direction to occur, and it's going to go towards it. Yeah. Yep. Yeah. It has no change. It will just get to equilibrium sort of quicker, but it won't cause it to shift one way or the other. It'll just kind of reach equilibrium. So because it's really not a reactant or a product, so it's not like you're adding more reactants or products to this situation. Again, it's just going to facilitate it getting to equilibrium quicker. So yeah. Other questions? Okay. Let's take a look at maybe one more here. That's what we just did. Let's do this one. I don't know if that two is on your handout or not, but make sure it is. All right, let's go. Let's increase the temperature. Let's remove O2. Let's add NO. Let's decrease the pressure. Let's see here. Let's Okay, so let's take a look. So in this case, it tells us it's endothermic. So again, that would mean we would have a delta H that would be positive, and we would consider heat to be a reactant in this particular case. That means for the first one here, if we increase the temperature, that'll be like adding more reactants, should kick off the forward direction and should head away from that side to the products. Any questions on that one there? Going to remove O2. O2 is over here on the reactant side. So when we remove O2, we essentially will then have more products than reactants. So that's going to kick off the reverse reaction and cause it to go towards where we removed it from. Or if you just want to think about it, you made a big hole on that side, you can need to fill it up with something, right? So that's a good way to remember it as well. If we add NO, again, that is a product. So now, again, more products than reactants, going to go away from that side, going to really kick off the reverse reaction in this case and head to the left. We decrease the pressure. That means the volume will increase. So we actually want big volume, more gas molecules. In this case, when we look at it, that's actually two gas molecules there, and that is two gas molecules as well. So that's going to be a no change as we got equal number of gas molecules basically on both sides. And lastly, adding a little N2. That's reactant side can go away from the side we added it to, causing us to have now more reactants than products, causing the forward direction of this reaction to basically occur. Any question on Le Chatelier's principle? Yeah. Good deal. That is this chapter 13. Yeah, sounds good. All right. That is the last chapter there of our first exam. Yeah. So scheduled for a couple of weeks, maybe. Not next week, but the following week, I think. Yeah. It's chapter 14, which will start exam two information. Again, a reminder, exam two is the exam most people have trouble with. So I say we're getting into troubled area, but we're getting into some interesting topics. Another interesting thing about chapter 14 is in your textbook, they just put everything into chapter 14. So I would say in most textbooks, chapter 14 is two separate chapters. So we're going to kind of treat it like that. So we're going to kind of do chapter 14 part one notes as we maybe looked at it. And that'll be almost like a chapter in itself. And then we'll do part two. And that'll be kind of like the second chapter and stuff like that. So we will be on chapter 14 for a very long time. It will seem like never ending chapter, but it's sort of like two chapters in one in this textbook. All right, so chapter 14 is about acids and bases, and let's talk a little bit about acids and bases. Acids have a sour taste. Vinegar, for example, major component is acetic acid. Citric fruits have citric acid. Acids are really things that can produce, as we will see, H plus ions in solution. H plus ions are hydrogen ions. One of the things that you should understand in acid-base chemistry is H plus, which is the hydrogen ion, and H3O plus, which is the hydronium ion, which is a polyatomic ion, are essentially the same thing. They are used interchangeable, both in formulas, both in equation and reactions. I would say nowadays people kind of use H3O plus a lot. I use personally H plus a lot. So really anywhere I put H plus, you could kind of put H3O plus in its place, and it basically means the same thing. It's really the acid part of the solution, and it can be used, kind of in interchangeable with each other. They also will call, as we'll talk about, H plus is sometimes also referred to as a proton in acid-base chemistry. And that again is because, as you may remember, hydrogen has one proton and one electron, but no neutrons. So the only way you become positively charged is to lose an electron, and that leaves hydrogen with just a proton at that point. So it's sometimes referred to as a proton, also in acid-base chemistry. Acids tend to react with certain metals to produce hydrogen gas, as you may remember in a classic reaction known as a single replacement reaction. Yeah, when you take something like zinc metal and it reacts with hydrochloric acid, it will kick out the hydrogen there and make some hydrogen gas, some bubbles, and the zinc and the chloride will come together here. I'll balance it like I'm in chemistry class over here. Remember, in order for this reaction to take place, right, whatever is coming in needs to be more reactive than what it's replacing, or it will not happen. They also react with carbonates and bicarbonates to produce carbon dioxide in a reaction. You may also remember, perhaps from Chem 50, a little hydrochloric acid plus some, we'll go with sodium carbonate, why not? Going to do a little double displacement reaction, right? We're going to switch partners. And the result of that is you'll end up with H2CO3 and a little sodium chloride in this particular case. Excuse me. And we could do a little balancing there as well. But that carbonic acid will very quickly go through a decomposition reaction and produce water and our CO2, which is how that gets produced in that case. Bases, on the other hand, feel very slippery. A lot of soaps and like drain cleaner type stuff are bases. You could go and buy some straight up sodium hydroxide at Home Depot to clear your drain. A lot of warning labels on it. But a base, as we will talk about, is really something that will produce hydroxide ions in solution. So something that's able to produce free OH minus solutions is, again, basically your classic definition of a base. before I go too far, just to make sure everybody's on the same page in terms of acids. Let's just talk a little about acids and nomenclature, right? So if you want to name an acid, it all is about whether or not there is oxygen, right? So if there is no oxygen, your acid name starts with hydro something ic acid, like HCl in the aqueous form is hydrochloric acid, right? HBr in the aqueous form, which is typically what you find acids as, and you typically put the aqueous symbol next to it, the AQ. That is hydrobromic acid. The cation for all acids is H plus, is the positive guy for all acids. The negative guy is the missing part there, is the anion part of it. If you do have oxygen, your acid will contain one of those polyatomic ions that everybody loves. And as you remember, those polyatomic ions basically end in one of two ways. It could either end in 8, and if it does, your acid is something ic acid. So if you have HNO3, that is NO3 minus, which is nitrate. This would be nitric acid, right? You have H2SO4. SO4 2 minus is sulfate. This will be sulfuric acid. No hydro with somebody that has oxygen, which are known as oxyacids. If your polyatomic ion and it contains oxygen ends in ite, which is the other way those guys end, your acid name is OUS acid. So if you have HNO2, that is nitrite, that is nitrous acid. H2SO3. SO3 2 minus is sulfite, that's sulfurous acid. Good reminder. Hopefully, I hope it's just a reminder of how to name acids so you don't go like that thing over there, that acid over there, that thing. Any questions on that there? All right, let us lay that up for today.